Okay, some tips for 13. 13. Well, the normal line you know is perpendicular to the graph. So if this is your graph, this is your normal line. In A, you simply need to find the gradient of the tangent first, which is f dash of 2. You're given that it's at 2. You have to differentiate f and then plug in 2. And I'm sure you remember this fact about normal lines, about perpendicular gradients in general. Then you simply state the straight line as you would with a tangent. In B, you, well, both axis intercepts, zeros, and the y-intercept, something that is quite easy to compute actually. In C, you have to compute the angle at which the graph intersects with the x-axis. So in B, you found this zero, this intersection with the x-axis, and we seek this angle here. The angle, well, if this is the gradient corresponding to that tangent, then there is this very important relationship. The tangent of the angle is the gradient, okay? This being phi, you can use this relationship to compute the angle. M, of course, being the gradient, so the derivative evaluated at the position of the zero. In D, find the exact x values of both stationary points. That should be straightforward, I think. Stationary point means f dash of x is 0, so you set this equation equal to 0. Alright, that's 13. Then 14. Here we're given an expression with a root and a product. You're going to need product rule and chain rule, both together. In A, you need to compute the 0. Another word for axis intercept, x-axis intercept. I didn't mention it before, but it's simply f of x is 0, right? Factored form, you've already got it in factors, so you set both factors equal to 0. In B, you obviously need to compute the stationary point, which means that you set the derivative equal to 0. You might actually get 2. No, you won't. Okay, so one stationary point, this is going to be the maximum. In C, the region enclosed in the first quadrant, it is going to look like this. When you plot this, I mean, you can always plot this on your calculator, I believe. I trust you realize this. When you plot this, you'll see it looks like that, okay? So I'm talking about this region here, and if this region revolves about the x-axis, you'll simply get pi times the integral from 0 to t, this being t, of f of x squared with respect to x. F of x squared is actually very convenient because it gets rid of the square root, right? So it's actually an easy problem. D is a lot harder because in D you need to compute the area, and it is quite demanding to, it is actually very demanding to compute this antiderivative. I gave the antiderivative and ask you to prove that it's true. So to speak, technique 1, okay? You differentiate capital F of x, which is a bit challenging but should be doable. Once you've done that, it's obvious that you simply compute this integral, and using the given capital F of x, you can, well, just compute without actually proving it, even if you are unable to do that, okay? That was 14. Now for 15. In 15 you're given two graphs, and if you plot this, okay, I didn't actually prepare that, but this is going to look like this. This is, oops, that's not what I intended to do. Alright, so this should be what g of x looks like. Yes, and f of x would probably look like, oh, I didn't plot this. Why does this not make sense? Well, okay, e to the negative x would look like this. Multiplying this by negative 2x. Well, this basically means we're still down here, but negative, okay, this looks probably like this. Yes, now it's making sense. It's a bit ugly, I apologize. Okay, and what I want to compute, alright, these 2 points here. I know it's ugly, but you'll manage if you plot this on your calculator naturally. This is going to be easy. I tried to do this without plotting it, but that was perhaps a poor idea. Okay, A, where do the graphs intersect? I'm sure you remember this. I was a little bit astray. Actually, it wouldn't have been necessary to plot this. Okay, it's this, and then you compute x, and you can certainly compute the 2 points of intersections. Then the point of inflection of f, you should be able to recall that this is the second derivative being equal to 0. And in C, the 2 graphs enclose a region in the second quadrant. Now, this is why I made such a fuss here, because I know that this is going to be important. Okay, this is in the second quadrant, first quadrant, second quadrant. Well, basically, this is simply an integral from t to 0, as t is going to be negative. It is going to look like that. Actually, this is solving d. Sorry, this is messy. This is what I meant when I said I actually need to script this, and I try to do without now. This is d, and what we integrate is, well, probably f of x minus g of x with respect to x. Please look this up. If this sounds unfamiliar, this is an important concept. The area between 2 graphs, you integrate the difference. Okay, it's not very tricky, but you might have to revise this. And in C, we are asked to compute the angle up here. Okay, this is the same reddish region. The angle at the top, at the leftmost vertex. Yes. So here, it's comparable to what you already did in 13, where you also computed an angle. You can translate these gradients into angles twice. And then simply compute the difference, okay? As we would here, first angle, and we simply subtract the second angle. What we're left with is the angle we actually want to compute. Alright, well, this hasn't been perfect. I hope it was nonetheless useful. The idea is that you watch this video if you encounter problems. I hope I could give some ideas, the strategies you need to solve these problems. Try to figure it out. If there are questions unanswered, please post them in the forum. Thank you very much.